bouncing, yeah, that's important.
Was it bouncing the other day?
I didn't do sound yesterday, yesternight, as the saying of Isaac goes. I will begin with a word of prayer. So, dear Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, and I just pray that you just help us to make the most of this time. Lord, help the students as they prepare for their test, that they just study the right things and just be able to understand what they need to, Lord. In my prayer, Lord Jesus. Amen. So, yes, we are on to chapter 4, and this book is the way he does the algebra in chapter 4. It's really quite beautiful and sneaky. So he essentially has found a way to roll all of the combinatorial nastiness of developing the wedge product into the determinant, which is really nice. It's a really nice approach. But I think what I'm going to do today is I'm going to take a slightly more formal approach, and for the most part I'll try not to construct, probably will not actually do what he's done in the book today. Maybe next time I'll do it, but today I want to just start with the next thing that you probably haven't thought about, which is dual space. Right, what is dual space? So we have to develop some algebraic preliminaries here. Once we get done with that, then I'll get back to calculus again, okay? And what we're after today is to describe what is a differential form. And so differential forms are very interesting, and we'll see what they are as we go on here today. Dual space. So if V is, a vector space over the reals, then V dual is equal to the linear transformations from V to the reals. Right? So this is going to be alpha mapping from V to the reals such that alpha is linear. So that's what you might call a dual vector. It's also called a linear functional. So we studied this in linear algebra. We learned that the dual space is itself a vector space. For a finite dimensional vector space, it's isomorphic to the vector space originally, and so we can talk about a dual basis. So if beta, let's say v1, v2, vn is basis for v, then beta dual, and here up and down indices is going to matter, v upper 1, v upper 2, v upper n. Tell you what, I'm going to, instead of using v's, no, it's too late, I already used v's, is basis for v dual. And the definition is just this. V upper I acting on V lower j is defined to be Kronecker delta ij. And then you extend linearly. One of the things we learn in linear algebra is that if you define a mapping on the basis and then you extend linearly, this uniquely defines the map. And so this uniquely defines the dual basis. And we can use dual vectors in connection with calculating components of vectors with respect to the basis and many other things. Let me just show you that. So what does a dual basis have to do with components? Little theorem. If we have x is equal to, say, the sum I equals 1 to n of x upper I, v lower I, then x upper I is equal to v upper I of x for each I. This is like one of the fundamental theorems about the dual basis is we can use the dual basis to pick off components of vectors, all right? So how do we prove this? Travis is not here, so I can prove things. Sorry, and not feel like I'm misbehaving. All right, so all I need to do, really, is to let v upper j act on x, right? Then that's going to be v upper j acting on the sum, I equals 1 to n of x upper I, v lower I, right? But by linearity, I can pull out the sum, and I can pull out the constants, x sub I, and then that gives me vj acting on v lower I. But by definition, what's that? This is the Kronecker delta, right? This is Kronecker delta ji. What happens? So do you know what I'm talking about, Tori? I mean, what delta ij is? Do you know what this thing is? Or am I just snowing you over? 'Cause you should ask me questions if I say stuff that you haven't seen before.
I've seen it before, I just don't know if I've ever actually fully understood it.
Okay, so what this is it's 1 if I is equal to j, and it's 0 if I is not equal to j. That's all it is. It's just a combinatorial symbol to denote that it's going to be 1 when the indices match, and it's 0 otherwise. So if you think about that, when you have a sum over I, right, j here is fixed but arbitrary, and so that Kronecker delta ij, it's always 0 except for one special case, which is when I is equal to j. So it kills the sum, and it just leaves you with x upper j, right? And that proves the theorem. So the dual basis is useful for calculating components of vectors with respect to a basis, right? Now, so let's specialize a little bit. Rn, right, we could say it's the span of E1, E2, right? En. So we can talk about Rn dual, right? So that would be the span of E upper 1, E upper 2, E upper n. That's the dual basis, the standard dual basis. Now, so like E, if we take E upper I and we let it act on x, then it gives us x upper I, right? By the theorem I just proved, right? But how else can we obtain the ith component of a vector in Rn? This is also equal to x what? Right, it's x dot ei, right? Or we could write that as ei, right, dot x, because the dot product is commutative, right? So as a matrix product, this is equal to ei transpose times x. So for Rn, which is I use Rn is what kind of vectors? It's what are they? They're how many rows? How many columns? N row. Yeah, n by 1, right? So for Rn equal to n by 1, it's natural to think of Rn dual as R 1 by n. But that's a lie. Okay? That's a lie. That's an identification. That's like saying a linear transformation is its matrix. Is a linear transformation its matrix? Well, no. It corresponds to the matrix. In the same way, a row vector corresponds to a dual vector. You see, so here's the difference. E upper I is a function from Rn to R. all right? Whereas E lower I transpose is a row vector. All right? Now, in fact, any dual vector in Rn can be rewritten. I mean, if you look at this, theorem, if we have alpha is an element of, the dual space to Rn, then alpha of x is equal to, let's say, a dot x for some a in Rn. In particular, what is, in fact, what's a? You do what's called alpha sub 1, alpha sub 2, alpha sub n, although I've seemed to have just introduced a notation. All right. Where alpha is in fact equal to the sum, I equals 1 to n, of alpha sub I, e upper I. I'm sorry, I seem to have found a way to wrap up a bunch of different results into this theorem. But all I'm really saying is that the dual basis is in fact a basis. I haven't proved that yet. You can prove that the dual basis is a basis for the dual space. In other words, every covector can be built from the dual basis, all right? And what should this alpha I be? Let's work this out. So what's alpha? If we take alpha of ej, right? Then, I'm sorry. What we should do is we should study, let me just look at the sum. I equals 1 to n of alpha I ei, e upper I, right? Let's let that act. I mean, this is a sum of dual vectors. I mean, it's a sum of linear transformations, so it's again a linear transformation. We can let that act on a vector and see what happens, right? So what happens if we feed this, and we've learned by now that working with an arbitrary x as a drag, we should just look at a basis that fixes everything we need to know. So let's look at the jth standard basis and what happens when we do that. This is just what? Well, this is going to be the sum. I equals 1 to n, alpha I, e upper I, e lower j. This is just, how we add together linear maps and evaluate them, pointwise evaluation. What's that? Well, this is, it's almost the same stupid calculation again. Kronecker delta ij, right? So we get alpha sub j. So if you tilt your head and squint, what this calculation I just did shows you is that we can write any alpha in the dual space, all right, then alpha is actually equal to the sum I equals 1 to n of alpha acting on e lower I, e upper I. So this is how to build. This is how we can build an arbitrary dual vector from its values on the basis. All right. Just like the corresponding formula for a vector, I didn't quite write it this way, but this theorem restated to mirror the boxed equation I just did would be x is equal to the sum, right? I equals 1 to n of e upper I acting on x, e lower I. So this is the corresponding formula for vectors. So so to get the component of a dual vector, we let the dual vector act on the standard basis or the basis. To get the component of a vector, we let the dual basis act on the vector to pick off the component. But in both cases, they play the role of like selecting components with the proper interpretation. Okay, so that's just your, I need to talk about dual vectors because we build lots of things from dual vectors, all right? Now, any questions about this? I can blather on about this for like hours, but that's linear algebra, you know? I think that's enough for us to at least be aware of the definition and some of the basis ideas. The principal application we have in mind is not actually Rn. So what's happening here is I'm going to take a second. I'm going to talk about tangent space and the dual to tangent space. All right. We're going to look at that for a couple minutes, and then we're going to shift gears. We're going to go back to abstract linear algebra for a while, and then towards the end of the lecture, we'll go back again to talking about calculus and what are called differential forms on a manifold. Right. That's where we're going. But next is what's the dual to tangent space? So if we have M a manifold, all right, either in the sense of chapter 3 of McNerney or the more abstract kind I've talked to you guys about, right? Then we have that the tangent space to a point in the manifold is what? This is a real n-dimensional, I'm sorry, I guess m-dimensional. I can't ever make up my mind. Is it m? Is it an n? You guys keep me on the straight and narrow, though. We said m, right? So m-dimensional vector space, right? And we learned that we would like to say that the tangent space to P at M is, what is it? It's the span of partial x upper I at P such that I equals to 1 to dot 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 M. And here we have that, you know, P is an element of U where U comma x upper I is an element of the atlas of M. In other words, this is a coordinate chart which contains P, right? You find coordinates near P, you can calculate the partial xi1, partial x1 through partial xm. These form the basis for the tangent space there, right? And so we can actually build those either from the parametric or from the implicit viewpoint. McNerney describes how to do that explicitly for his geometric sets in chapter 3, right? So but anyway, that's a real n-dimensional vector space. So this general construction of dual space I just talked about makes sense here. And we can talk about the dual space. So a lot of times people don't even write the parentheses. We'll just say TPM star, all right? This is the so-called cotangent space. Cotangent space. All right? And so in this case, we have special notation. The dual basis, so that, let me give a name. Let me say that this is the standard. I'm going to call this thing, you know, this is basis beta, if you don't mind, all right? So the dual basis to that basis, beta dual, is the following. It is D, and, you know, I debate. I don't, I either got to put he puts the P over here, and I guess that's fine. I sometimes in the past have put P over there, so don't read too much into that, okay? I can't make up my mind where the P should go. It kind of depends on viewpoint. This is nice. This is nice for the same reason it's nice to write the P here, because if you strip off the P, you can kind of think of partial xi as what? This is a section of the tangent bundle over U. it's a vector field on the coordinate system. In the same way, you could strip off the p here and think about dxi as being like we don't even have a name for it yet. It wouldn't be a vector field, right? Maybe you call it a form field or a dual vector field. But anyway, if you strip off the p, you could think about this anyway, be where I am, do what I'm doing. So dual basis, such that I equals to 1 to m, right? And what is the, by definition, we have what? dxi partial xj, right? At the point P is equal to Kronecker delta ij. Now this begs some notational questions because we've defined, you're like, haven't we already done that notation already with a different meaning? Yeah, we have. We talked about the push forward, right? And xi is a function, right? We can take the differential of the function. So let's see here. I'm not sure I should talk about that right now, but let me just get into it. So let's see here. The other way to interpret this would be, what did we say? How'd it go? df, remember df at the point P, acting on x, what was it? Have we even done this yet? I don't remember. Maybe we haven't. I mean, see, I know this is x of f. My question at the moment is that actually something I've done here yet? I don't know if it is. I mean, we talked about the push forward. We talked, so I think we talked about the push forward, and this wouldn't quite match the push forward, would it? No. So there's something sneaky that goes on here. So first of all, what is f? F is a function from, let's say, the manifold to the reals, all right? So if we take this, if x is if we think of this as the push forward under f, right? Which we've used his notation is what? F star p is what you guys might be looking for. But I use the notation d sub pf for that, right? And I mean, this is not quite it. It was, when you think about this particular context, the question is, here we have partial xi in the basis of the tangent space, right? What's the basis for the tangent space to the reals, right? Because remember, dpf should be mapping from the tangent space at p to m to the tangent space at f of p to the reals. Well, what's the tangent space to the reals? It's kind of silly. It's just like span of, let's say, ddt or something. It's one-dimensional. So from that viewpoint, from the viewpoint of push forward, this isn't quite right yet. I still need, this is at the point P, this is at P, and there's a ddt at f of P missing here. But in this special case, it's customary in differential geometry to drop the ddt to make the identification that ddt at f of P is identified to be 1. All right? So with that convention, the push forward actually, in this context, just becomes that dpf of x is equal to x of f. All right. So again, notation, using that dpf is just another notation for the push forward at p. So with this notation in mind, is the dual basis consistent? Is the dual basis consistent with everything else that I've laid on the table? Right? Because now I have a different way to calculate. Let me just put it out there. I can calculate this meaningfully now, right? dp x upper I can let that act on the vector field partial xi, upper j rather, at p, right? I'm telling you, according to the identifications that we've made, that must be equal to what? That must be equal to partial xj at p acting on, well, x upper I, which is the function here, right? This is f, quote unquote, equal to xi. That's a mapping from, from the manifold to the reals. Okay, fine, for a subset of the manifold, but you got it. But you guys have proved, right? We worked this out the other day, that this is nothing more than partial xi, partial xj, right? At p, which of course is Kronecker delta ij. So hooray! This is not, this notation that dx upper I is the dual basis to the coordinate vector field basis is a reasonable notation. It's consistent with other constructions, namely the push forward paired with this identification that in one dimension we identify ddt with 1. Now, this isn't just me. This is like most books, okay? This thing I did here. But most books won't tell you they did it. They just do it. And then, at some point you're supposed to understand these things. All right, so this is pretty neat. The dual space is built from differentials. So, like example 1, R3, we can talk about, the tangent space to a point at R3, right? It's built from, it's got partial x, partial y, partial z at the point, This is the basis for the tangent space at a point to R3. What's the basis for the cotangent space at a point to R3? It's dx at p, dy at p, dz at p. No one writes this at p. Very soon we just start writing dx, dy, dz. So dx, dy, dz, these are the basic dual vectors to the cotangent space at a point in R3. Oh yes, thank you. And I can't help it. I got to put, it just bothers me. Those parentheses are optional, I suppose, but anyway. Yeah. All right. So these are the principal, these are the vector spaces we're most interested in, Rn, right? It's dual. And the tangent space, and it's dual the cotangent space, all right? So with that, we talked to you a little bit about multilinear algebra. So what's multilinear algebra about? You might guess it's the study of multilinear transformations, all right? So particular, if you have T, which is a mapping from, say, V cross cross V dual, cross v dual, cross da 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 da, cross v dual, and suppose that there's R of these and there's S of those, and its output is a real number, right? Such a thing as this. Something that's a mapping from a bunch of copies of a vector space and a bunch of copies of the dual space to the vector space to the reals. If it's linear in each entry, this is called a tensor. More specifically, this is a multilinear map. Or tensor. All right. And I mean, long story short, so if I don't want to belabor the theory here that much, but if V is the span of E lower I, and if V dual has dual basis, span E upper I, like that, then I can build any tensor from what's called the tensor product of these dual bases, these basis and dual bases. In particular, I can write that T, here you go. I'm not sure I really want to do this. I'm too far in now, though. Sorry about this. Very sorry about this thing I'm about to write. So sorry about this, but it's what's done is done. I1, I2, da 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 dot IR equals 1 to n, summation J1, da 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 dot JS, and then you got 1 to n T, and T has to eat. What are we going to feed it? We're going to feed it E upper I1, dot 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 E upper I R, comma E lower J1, comma dot 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 dot, comma E lower JS, close parentheses. So I'm feeding this multilinear map a set of dual basis vectors and vectors, all right? So this is a number. And then, in fact, we can meaningfully write over here E I1 tensor tensor E lower I R tensor E J upper 1 tensor tensor E J upper S Yeah, and this kind of stuff, we tend to use EI as an arbitrary basis. I know it's at odds with using it as a standard basis, I'm sorry.
Oh yeah, you switched the R,
I got these exactly backwards, don't I? All right. I either got to turn this chalkboard, listen to me. So there's two ways to fix this. Do we want to put stars up there? Or do we want to fix all the indices? I say that we want to fix the indices because I like to put the V's first. I don't know. I mean, I'll do this one. I wish you guys had said something about, like, I don't know, forever ago. Let's see here. I mean, it's an all or nothing kind of deal here. There's a sort of a conservation of indices going on here.
Wait, so why did the V star bases go
Well, the E lower i's are in V, and the E upper i's are in V dual, so that's the order they have to be fed to the tensor.
Right, for there. Why are the other way around?
Oh, this right here is itself a tensor. So I'm expressing T as a sum of other tensors with components that are given by T acting on the basis elements. This is the analog to the boxed equations over there for vectors and dual vectors. But there is an abuse. See, because I'm suggesting, and let me show you what the definition is, and then I'm going to stop this stuff pretty soon because, well, anyway. I was really trying not to do this today. I'm sorry, guys. I will eventually learn how to not say things.
I'm just going to replace that expression with T equals
Okay. But this is something that we're going to define to be and let it act on, x, say x1. Maybe I should use v's or something. v1, v2. Why am I doing 2 all of a sudden? v1, vr, and alpha 1, alpha s. All right. That is by definition what it has to be. That's EI1 acting on V1, EIR acting on VR. And then how can I produce a number using this vector and this,
alpha 1.
right, it has to be alpha 1 acting on EJ1, alpha S acting on EJS. All right. You can, it's actually almost immediately clear that this thing I just defined is in fact a tensor. It's linear in every entry. You can pull constants out. And if you work at it a little bit, not much more than I've already written most of it, but you can prove, in fact, that these things, with those things, you can build any tensor by that formula. Now, typically in physics, when we talk about a tensor, we'll say that, it's this. We don't say what I just said. We'll just say the classic language in physics is to refer to it by its components. So the components of this tensor are this: T, lower I1, I2, IR, and then upper J1, I'm including a 2 all of a sudden, JS. These are the components of T. Of course, that's with respect to this basis. And you can tell what kind of tensor it is according to how the components transform. Right. For example, the most basic kind of tensor is just a vector or a dual vector, and those transform differently. If you look at the components, x upper I change basis, if you look at the components alpha lower I and you change basis, they have different basis change properties. And physicists distinguish different kinds of tensors according to their different transformation rules under change of coordinates. We, on the other hand, like to look at them abstractly in terms of like linear algebra and basis and so forth. T is T. Whatever basis you choose, T is T. Right? All right. Anyway, that in a nutshell is what a tensor is. So we can talk about tensors over a manifold at a point. We just replace this abstract vector space V with the tangent space, and replace V dual with the dual space, the cotangent space. And then you can talk about tensor fields. What's a tensor field? This is the pointwise assignment of a tensor at each p, point. Each point along some object, And by object, I mean it could be manifold, right? It could be a submanifold, right? It could be like a curve, etc. I mean, we can talk about, just like we can talk about a vector field over the whole space, or we can talk about a vector field along a curve, we can talk about a vector field along a plane. All of these options are also available for tensors. You can think about attaching a tensor to each point in your space, and this is a tensor field. You can also meaningfully say that that's the section of a tensor bundle. Guess what a tensor bundle is? This thing, the set of all such things, forms a vector space of somewhat large dimension, but you can glue one of those at each point over your manifold, and then you get a projection. You can build sections of that thing. That's called the tensor bundle. Anyway, we don't need to do that. Just saying you could. So we do some things with tensors later chapters, which is why it's important for us to have this discussion right now. Like the metric tensor, which you measure distance with, it takes in a pair of vectors and outputs a number. So it's the metric tensor is like r equals to 2, s equals to 0. But we're actually most interested in working with things that are more like this. All right, and here there are k of these. All right, and if we have t of, say, x1, x2, xk, I'm using x for a vector all of a sudden. I guess let me at least be consistent, because I'm using x for a chart here. That's bad. Let me not do that. Bad, bad, bad. 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 So if we instead use v's, v1, v2, vk, if the tensor, suppose this is a tensor, all right, you could also call it a k-linear map in this case, because it's got k inputs, all right. If it has the following property, if it has that this is equal to the sine of sigma t of v sigma of 1, v of sigma of 2, v sigma of k, all right? If all that happens for you, then this is said to be a completely antisymmetric tensor. Right.
Oh, sigma is in SK.
Yeah, so yes, and thank you. Here, sigma is an element of the permutations on k elements. So I'm sorry, guys, I should stop and tell you. So I know, Travis, you have not had abstract algebra. This is one of our examples in abstract algebra. Permutations, but you know what they are already.
Yeah, I know the concept.
You know the concept of a permutation. So what this says is you take these entries and you scramble them, but they're all still there. They're just reordered. And then this sign will either be plus or minus depending on whether that permutation is what's called even or odd. Now this is entirely equivalent to saying that anytime you take any two slots here, could be any two, and then you flip it, you get a minus sign from doing that. That is entirely equivalent to this formula in terms of permutations. To actually prove that, I don't want to do. That would be combinatorics, and it would be a drag, because I'm not that kind of person. Anyway, so, but this has a name. Here we say then that T is an element of lambda upper K of V. And this makes, that is, T is a K-form over V. Or, I mean, I guess over V. Maybe it's on V. I don't think it's in V. It's definitely over or on. Now, something beautiful happens with these K-forms. Is we're able to trade these circle crosses, these tensor products, for something more elegant called the wedge product. It turns out we can build these K-forms from what are called wedge products of the basis forms. And this is done systematically and rather nicely in McNerney. And I'm not going to do that today because I think you've had enough of this kind of math for today. What I want to do is describe to you the K-forms over R3. And I want to show you how we can do calculus with K-forms over R3 for the rest of the lecture, okay? And we'll worry about abstract, well, maybe I'll do some of the definitions as we go on here. Depends how much time I have, I don't know, but I should get a watch. We're okay. So here, as we go on, we'll be sporadically discovering homeworks as we go, because I'll get to a calculation I don't want to finish, and then I'll say homework. So then I'll try to remember to actually make those into honest to goodness problems. Let's see here. Now, it's unfortunate, but I don't have like, you know, we have vectors and we have vector fields, right? But it's a common practice in mathematics to call the form, right, which I would like to think of in the same way I think about a vector at a point, the same as like a form field. Like not many people would say form field, but often when we talk about differential forms, we're actually talking about a form field. It's an application of a differential form at each point. It's a form at each point over the tangent space, all right? But we'll just say differential forms for both the thing at a point and the field idea, just because that's the common usage. It's unfortunate that we don't have a more common distinction between those terms, but it's just not the case. Okay, so R3. I want to talk about the exterior algebra. On R3. So the basic thing is we have 0 forms, we have 1 forms, we have 2 forms, and we have 3 forms. Right. So this is a little bit out of order. I mean, technically speaking, I should really take another 20 minutes and develop a little bit more abstract multilinear algebra here. Tell you what, I will do just a little bit more in that regard so that we don't put the cart entirely before the horse here. I won't prove these things because that would require the development in McNerney that I'm not willing to commit to at the moment. But this is the ultimate outcome of those things we construct in chapter 4 to start, and that's this, is that if we have alpha, which is a K-form, oh, he has sub K finally, K-form over V, And if we have beta, which is a, he uses L form over V, and gamma is a M form over V, all right, then you can do this wedge product with them. So alpha wedge beta wedge gamma is equal to alpha wedge beta wedge gamma. And beta wedge alpha is equal to minus 1 to the KL alpha wedge beta. And the pairing, alpha comma beta maps to alpha wedge beta, is bilinear. Now, of course, the thing that you might find a little bit mystifying at the moment, this is proposition 4.28. And basically, any construction of the wedge product is going to come down to producing these three features. These are the three essential features of the wedge product, is that it's an associative, skew commutative, bilinear mapping on K-forms. So what this is saying is that there's a natural algebraic structure. There's a way you can combine completely antisymmetric maps with, say, K inputs, and other completely antisymmetric map with L inputs, such that you get a completely antisymmetric map on K plus L inputs. I mean, that's the hidden thing in here, is that this alpha wedge beta is a completely antisymmetric tensor. This is a way of building a new completely antisymmetric tensor from two given completely antisymmetric tensors. There's a lot of combinatorics hidden in that, and it's all shoved into the determinant in what he does at the start of chapter 4. Very sneaky. I'll try to do that next time. Wait a minute. We have some classroom interaction next time. Once we get past that, most pleasant experience, then we'll get to that. But anyway, these things are true. Now, I can tell you this much. Like, here's one I can tell you for free. In terms of the relation with the tensor product, if we have alpha wedge beta, if these are both one forms, then that's just going to, well, let's base this one form. Let me keep it more explicit here. E1 wedge E2. What's that going to be? That's going to be E1 tensor E2 minus E2 tensor E1. I'm really reluctant to say much more than that because I haven't studied the combinatorial conventions in McNerney carefully enough to not make an error. But I believe that's consistent with his text. This is the wedge product for two one forms. This is how you put them together to get a corresponding antisymmetric thing acting on two inputs. But the cool thing is, it takes on a life of its own because we can just look at like the algebraic structure of it and study that. And that alone is fascinating. So I'm going to focus on that. Now that I hope I've said enough that you have some sense of what a wedge product is. Admittedly, we'll need to spend another couple hours really digging through it. So R3, what are the zero forms? And again, I'm going to make the abuse that these are actually, I mean, here I'm really, to be more clear, to be more honest, these are really form fields. But no one says that, okay? So smooth function. Smooth function F. All right, just smooth function from the reals from R3 to R. One forms. What do one forms look like? A one form would be something like alpha equal to a dx plus, well, tell you what, let me be alpha 1 dx plus alpha 2 dy plus alpha 3 dz. All right, that's a one form, where here alpha 1, alpha 2, alpha 3, these are themselves smooth functions from R3 to R. All right, that's what an arbitrary one form looks like. It's built from these guys. Two forms, beta, it would look something like beta 1, 2 dx wedge dy plus beta. Tell you what, let me do this numbering a little bit different to suit my purposes. We will say beta 1, and I would prefer to use the basis dy wedge dz plus beta 2 dz wedge dx plus beta 3 dx wedge dy. All right, and I need to erase this. It's in my way. Let me just stop saying it. All of the component, all of alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3, these are all smooth functions on R3, okay? Now, 3 forms, there's just one of them. And it looks, well, there's a lot of them, but one of them up to a scalar multiple by a function is something like g dx y dx wedge dy wedge dz. This is also called a volume form. So you got 1 forms, you got 2 forms, you got a volume form, you have 0 forms. This is the name of the game. These are what's there. And the thing is, that's it. Because one of the things you can prove from these pretty quickly is that if we have alpha wedge alpha equal to minus alpha wedge alpha, right, then alpha wedge alpha equals to 0, right? That would be the case for what? If the degree of the form is odd, then you actually get a minus, right? If you had a 2 form wedge a 2 form, it wouldn't have to be minus again. But if, in particular, dual vectors, when you wedge them, they have to, if you take the same dual vector and you wedge it with itself, it comes back to minus under that rule, which means the wedge product of any, let me just write it. dx wedge dx is equal to dy wedge dy is equal to dz wedge dz. And you know what? They're all 0. In contrast, dx wedge dy is minus dy wedge dx. dz wedge dx is minus dz wedge dx wedge dz. Does this look familiar? dy wedge dz. What does this remind you guys of? Oh yeah, cross product. Or quaternions. Either way is good. But those are both great analogies, and they're both useless. Because they're not apt. This is different. I mean, it's the same pattern, yes, but the wedge product of 2 1 forms is a 2 form, which is a different object. In contrast, when I multiply 2 quaternions, I always get a quaternion back. If I take the cross product of 2 vectors, I get back a vector, right? And also, by the way, the cross product of vectors is non-associative, whereas this wedge product is associative. So they're quite different things. Now, there's some games we should play here. This is what's called the work form. I do omega sub vector, alpha 1, alpha 2, alpha 3. So this is the work form of, say, f vector, or you could say alpha vector if you like. Alpha vector, which is the vector field with alpha 1, alpha 2, alpha 3. All right? Like in physics, yes. Work form. This, on the other hand, is the notation is sideways TIE fighter. Very overused symbol in my courses. But phi sub beta, this is phi sub beta vector. You know, this is the flux form